Welcome to the fifth lecture on Statistical Thermodynamics Part B. In this lecture, we will see about the various molecular partition functions like translational, rotational, vibrational, and electronic partition function. The following topics will be covered in this lecture. Mainly, we will see about the various components of partition function. In previous lecture, we have seen the relation between molecular energy, statistical weight factor, and molecular partition function. We have seen molecular energy is given by sum of translational, rotational, vibrational, and electronic components of energy, such that total energy can be written as EI is equal to ET plus ER plus EV plus EE. Let this be equation number 1. The statistical weight factor is given as product of translational, rotational, vibrational, and electronic components. And the total statistical weight factor is given by GR is equal to GT into GR into GV into GE. Let this be equation number 2. Using these two equations, we see that partition function is a product of its component. By definition, partition function is given by Q is equal to summation Gi e to the power minus Ei upon Kt. Substituting the value of Gi and Ei from equation 1 and 2, we will put for Gi product of all the components and for Ei summation of all the components. Now, if we consider these energies as independent of each other, then these terms will factorize into different components. So we can write Q is equal to summation of Gt e to the power minus Et upon Kt. Similarly, rotational, vibrational, and electronic terms. So we can write Q as a product of all the components of partition function, that is translational, rotational, vibrational, and electronic. Now let's see the expressions for allowed energy levels and their degeneracy. We know that in quantum mechanics, when we solve Schrodinger wave equation for different systems, we get the expressions for energy levels. When we solve Schrodinger wave equation for one-dimensional box, we get the expression for energy for translational energy, that is given by Et is equal to n square h square upon 8m Lx square, where n is quantum number and which has values 1, 2, 3, etc. Here n cannot be equal to 0. M is mass of particle, Lx is the dimension of the box, h is Planck's constant in all the cases. Here the degeneracy is equal to 1. The energy levels are non-degenerate. Similarly, if we solve Schrodinger wave equation for diatomic molecule as rigid rotor, we get the expression for rotational energy level Er is equal to Jj plus 1 h square divided by 8 pi square I, where J is rotational quantum number, I is moment of inertia, which is given by I is equal to mu r square, and mu is reduced mass m1 into m2 divided by m1 plus m2, and r is the bond length. Here J is rotational quantum number which has values 0, 1, 2, 3, etc. Degeneracy is also given by Gr is equal to 2J plus 1. Here also J is rotational quantum number. Now, if we solve Schrodinger wave equation for simple harmonic oscillator for diatomic molecules, we get the expression for vibrational energy level, which is given by Eb is equal to V plus half h nu, where V is vibrational quantum number and has values 0, 1, 2, 3, etc. Nu is the vibrational frequency. Here the degeneracy is again equal to 1. Now for electronic energy, the expression can be taken as delta E is equal to h nu, or nu can be written as hc nu bar. Here the degeneracy is equal to 2J plus 1. Here J is resultant angular momentum quantum number, which is determined by the Russell center coupling L plus S. We have also seen the difference between the energy levels of atoms and molecules. In case of atoms, we have seen that there is only electronic energy levels. In molecules, we have seen that there are electronic energy levels, and between these electronic energy levels are vibrational energy levels, and between these vibrational energy levels, which are given by these blue lines, there are small energy levels which are known as rotational energy levels. You see that all these energy levels are quantized. There is a large gap between these electronic energy levels, whereas for vibrational it is little less, and for rotational we see that they are very closely spaced. So we will see that in partition function we will introduce, instead of summation, integration in case of rotational energy levels. Let's start with translational partition function. We have seen that translational degree of freedom is 3, whether it is atom or molecule. This is because translation motion can be along the 3 principal axes x, y or z. So whether it is atom or molecule, in both the cases we have translational degree of freedom as 3. Now corresponding to these translation motion, we will be having partition function with respect to x-axis, partition function with respect to y-axis, and partition function with respect to z-axis. And the total translational partition function Qt will be given by the product of all these 3 terms. Now let us consider any one of these terms. Let us take translational motion along one direction, in one direction, say x-axis. Then the translational partition function along x direction will be given by summation g t. This is statistical weight factor for translational energy of ith energy level, e to the power minus et I upon kt, and this summation is from I is equal to 0 to infinity. So this is for x direction. Now we can write this in a simplified way. Qt x is equal to summation 0 to infinity. We can drop this I and write gt e to the power minus et upon kt. Here we require 2 terms. One is the statistical weight factor and another is the translational energy. So let's see what are its value. The statistical weight factor Gt is always equal to 1. That means the degeneracy of translational energy level is always 1. Now let's see what is translational energy level. Now when we solve Schrodinger wave equation for one-dimensional box, in quantum mechanics we have seen the translational energy for one-dimensional box. If we take one-dimensional box, this is the dimension along x direction. Let us take it as Lx, and the potential energy inside the box is taken as 0. That means the total energy will be equal to the kinetic energy or the translational energy. And the energy in that case is given by n square h square upon 8 m Lx square, where n is quantum number having values 1, 2, 3, etc. n cannot be equal to 0. H is Planck's constant, m is mass of the particle, and Lx is the dimension of this one-dimensional box. Now let us number these equations. Let this be equation number 1. Let this be equation number 2, 3, and equation number. We can get this equation by simply taking the kinetic energy formula also. Let us derive it. Et along x direction, that means the kinetic energy is given by half mvx square. Now we know that m into v is equal to momentum p. So in terms of momentum, we can write kinetic energy as px square upon 2m. Now according to de Broglie equation, wavelength is equal to h upon momentum. So substituting here, we will have px will be equal to h upon lambda x, or px square will be equal to h square upon lambda x square. Now we can substitute here and get the value of this kinetic energy. Now let us consider the stationary wave. For stationary waves, the path length Lx, this is equal to half integral multiple of wavelength. So lambda x has a value equal to, lambda x is equal to 2 Lx upon n. Square of this will give lambda x square will be equal to 4 Lx square upon n square. So we can substitute this value. Let this be equation number 5, this 6, this is 7. Now we will equate this equation 7 in 6 and we can get the value of px square. Let's see, if we substitute here, what do we get? We get this is equal to px square is equal to h square upon lambda x square. Lambda x square is in denominator, so this will invert and we will have n square h square upon, in denominator we will be having 4 Lx square. Now we can substitute, let this be equation number 8. Px square is equal to n square h square upon 4 Lx square. We will substitute this value in equation number 5 and we will get, substituting the value, we will get Etx is equal to px square upon 2m. On substituting the value of px square, we will have n square h square upon 8m Lx square. This is the very equation which we have written for the Schrodinger wave equation for particle in one-dimensional box, which is equation number 4. Now let us substitute the value of this gt and etx in equation number 2. Let's see, q t x is equal to summation 0 to infinity, we are putting gt as 1, e to the power, this will be minus n square h square upon, we have 8m Lx square, 8m Lx square kt. Let this be equation number, this is 9, this is 10. Now here the term, so we have substituted the value of gt and et in this equation. Now h square upon 8m Lx square kt. We compare the value of this with kt. Kt is the thermal energy this is very high compared to this. So the translational energy level will be closely spaced. They are not far from each other. So we can convert this summation, or we can write this summation in the form of integration. So we will replace summation by integration. We will have e to the power minus n square h square upon 8m lx square kt, and here the integration will be with respect to n. Now here these terms are constant for a given particle, so we can write for h square 8mlx square kt a single term. Let us represent it by alpha. So we will substitute this value. So qt along x direction is equal to integration 0 to infinity e to the power minus n square alpha d. Now according to standard integral, this integration 0 to infinity e to the power minus n square alpha dm is equal to 1 by 2 root pi by alpha. So if we substitute this value here for alpha, we will have 1 by 2. This is root of pi, that means pi to the power half. Alpha is h square upon 8 ml square upon kt, and alpha is in the denominator, so it will get inverted. So here we will have 8m lx square kt divided by h square to the power this root half. Now on solving this, what we will get? We know that 8 is 2 root 2. Lx square root will be Lx. Root of h square will be h. So what we will get? Qt will be equal to this 2 and this 2 will cancel. We will have 2 to the power half, pi to the power half. Okay, this has been converted to 2 root 2, so only we have root 2 here. M is there. We have taken this out. Lx square root is Lx. We have kt here. These are all to the power half. And h square we will have h, and here we will have Lx. Okay. So this is 2t to the along x direction. So we have got the value of, or the expression for partition function along x direction, which can be written as 2 pi m kt to the power half upon h lx. Here this is having the dimension of wavelength, and this will have the dimension of inverse of wavelength. Or we can write h upon 2 pi mkt to the power half. This is having the dimension of wavelength. It is represented by lambda and is known as thermal de Broglie wavelength. So we can write this as Lx upon lambda. Similarly, for y direction we will be having the same equation. Only difference will be here, it will be Ly. For pi we will have 2 pi mkt to the power half h ly. For z-axis we will be having 2 pi mkt to the power half h into Lz. And according to equation number 1, we have seen that the total partition function for translational energy will be, let this be equation number A, B and C. So the total partition function Qt, which is equal to product of Qt along x direction into Qt along y direction into Qt along z direction. On substituting these values, we will have 2 pi mkt to the power 3 by 2 h to the power 3 lx ly into lz, and this is nothing but this is equal to volume. So we have 2 pi mkt to the power 3 by 2 h cube into v, or in terms of this we can write it as Qt is equal to v divided by lambda cube. So this is all about translational partition function. Next we will see some numericals related to this. Now let's see the summary of translational partition function. Translational energy in one dimension is given by ETX is equal to n square h square upon 8m lx square. The statistical weight factor here is 1 because the energy levels are non-degenerate. Translational partition function along one direction, that is taken as x, is given by Qtx is equal to 2 pi mkt to the power half divided by h lx. Here m particle mass of particle, k Boltzmann constant, t temperature, h Planck's constant, and lx is the dimension of the box. Here if we see this expression, we know that this is a dimensionless quantity and this has the dimension of wavelength. So this quantity will have dimension of inverse wavelength. So h upon 2 pi mkt to the power half is known as thermal de Broglie wavelength and is represented by lambda. So we can write Qtx as along x direction as Lx upon lambda. Similarly, we can have the components along y and z, and the total translation partition function will be the product of Qtx into Qty into Qtz. So on substituting the values, we get Lx into Ly into Lz, which is equal to v. So the total translation partition function is given by Qt is equal to 2 pi mkt to the power 3 by 2 upon h cube v. We can introduce this lambda here, so we will have lambda cube. So Qt will be equal to v upon lambda cube. Now let's see a numerical based on translational partition function. Calculate the translation partition function of oxygen molecule which is confined to a 200 centimeter cube vessel at 298 Kelvin. The data given are B is equal to 200 centimeter cube, converting it into SI unit 2 into 10 to the power minus 4. The mass for oxygen molecule here has been taken as 32. We are converting it into kg, so we have 10 to the power minus 3, and this is for 1 mole, so fit 6.023 into 10 to the power 23. So we will get the mass of oxygen molecule as 53.130 into 10 to the power minus 27 kg. Planck's constant, we know the value. Then Boltzmann constant, we know the value. We will put all the values in this expression. On substituting, we get Qt is equal to 3.7 into 10 to the power 28. This means a large number of thermally accessible states are available in case of translational energy. This is of the power greater than 10 to the power 20. Up to it can be 10 to the power 30 also.
Now let's see about rotational partition function. As we have seen in earlier classes, rotational degree of freedom is different for linear and non-linear molecules. In case of atoms, there is no rotational partition function. We have seen that in case of atoms, we have translational partition function, and in molecules, we have translational, rotational as well as vibrational partition function. For linear, the degree of freedom is 2, and for non-linear, the degree of freedom is 3. Now let's see how we can write the rotational partition function. As we have written for the translation, in the same way we will write 0 to infinity. Here it will be gr. I term has been dropped here for convenience. E to the power minus er upon kt, where gr is the statistical weight factor for rotational energy level. Er is the rotational energy level. These are the two quantities we require for calculating the partition function. So let us see. The statistical weight factor for rotational energy level is given by 2j plus 1. That means the degeneracy of rotational energy level depends upon j, the rotational quantum number. For example, if j is equal to 0, then the degeneracy will be 2 into 0 plus 1. If j is equal to 1, the degeneracy will be 2 into 1, 3. Okay, sorry, 2 into 1, 2 plus 1, and accordingly the degeneracy will be 3. Okay, so you see that we can find the degeneracy of the rotational energy level just by using the formula 2j plus 1. Now let's see what is the rotational energy level. You all have studied in spectroscopy as well as in quantum mechanics the expression for rotational energy level. In quantum mechanics, we have seen that when we solve Schrodinger wave equation for rigid rotor, in which we consider diatomic molecule as a rigid rotor, we get the expression Er is equal to j plus 1 h square upon 8 pi square I. That is the equation number 1, 2, 3. These are the main equations which we will be substituting. Here I, you are all familiar with this moment of inertia. This I is moment of inertia, which is given by mu r square, where mu is a reduced mass and is given by m1 into m2 divided by m1 plus m2. So using this, you can calculate the moment of inertia, and substituting the value, you can get the value of Er. Here R is bond length. J is the main term, that is rotational quantum number, and it has value 0, 1, 2, 3 and so on. So this is the expression for degeneracy and energy for rotational energy. We will substitute this in this equation and we will get QR is equal to summation 0 to infinity GR is 2j plus 1 e to the power, this is j plus 1 h square upon 8 pi square I, and we are having this k theta. So this is equation number 4. Now, as we have seen in translational, this term h square upon 8 pi square I is small in comparison to the thermal energy kT. So the rotational energy levels, though they are far from translational energy, but they are still we can consider them as closely spaced. You have seen the different values of J. The gap goes on increasing. J is equal to 0, 1, 2, 3, etc. But still we can consider them as closely spaced. So this summation will again be replaced by integration sign. So QR is equal to integration 0 to infinity 2j plus 1 e to the power minus j plus 1 h square upon 8 pi square I kt, and here the integration is with respect to j, so we'll write dj. Here again we have these as constant for a given molecule, so this will be h square upon 8 pi square I kt. We can replace it by a single constant, let's say beta. This is equation 5, this is equation 6. We will substitute for this beta. So what we will get here is, we will get beta dj. Let this be equation number 7. Now for simplifying this, we will do some simplification here. Let us substitute for j plus 1. For this, let us substitute a single term, that is z. On differentiation of this equation, we can get the relation between dz and dj. So if we differentiate this, we will get dz. This is dz with respect to dj we are doing. This is j square. So we will have 2j. This is j, differentiation of j with respect to dj will be. So we have equation number 8 and equation number 9. So we will substitute this in equation 7. We will get QR is equal to integration 0 to infinity 2j plus 1 dj. Okay, for this we will write dz, and for j plus 1 we will write z. So we have e to the power minus z beta dz. And for this type of integral, the standard integration gives 1 by beta. So let this be equation number 10. So what will be the value of QR? QR will be simply the inverse of this beta. That means this will be 8 pi square I kt upon h square. For all the linear molecules, whether it is diatomic or polyatomic, this equation will apply, where I is moment of inertia, K Boltzmann constant, T temperature, and H is Planck's constant. This equation is valid only for, in case of diatomic molecule, if we see, it is valid only for heteroatomic molecules like HCl, NO, etc. In case of homoatomic, only half of this will be thermally accessible. That means for homoatomic, this equation becomes 8 pi square I kt. Only half of this will be thermally accessible. So we have, so in heteroatomic this value is 1 and this is 2 here. So in general form we can write, we can introduce a term known as symmetry number. So we can write QR for whether it is heteroatomic or 8 pi square I kT upon sigma h square, where sigma is known as symmetry number. And this is symmetry number is nothing but, suppose we are having the homoatomic molecule, you can take N2, O2, etc. Suppose we are having N2 molecule and we are rotating this molecule along this axis. When we rotate it through 180 degree, then we get an orientation which is indistinguishable or same as that of the original one. So while rotating through 360 degree, we get two such indistinguishable orientation, which you have learned in group theory. So here the symmetry number is nothing but it is number of indistinguishable orientations which we get on rotating through 360 degree. So for polyatomic, the expression will be little different for spherical, asymmetric and symmetric top depending upon the moment of inertia.
Just now we have derived the expression for rotational partition function for linear molecules, which is applicable for both diatomic and polyatomic molecules. It is given by QR is equal to 8 pi square I kT upon sigma h square, where I is moment of inertia, K Boltzmann constant, T temperature, sigma symmetry number and H Planck's constant. Here in this expression, QR is a dimensionless quantity and T is having the dimension of temperature. So this quantity h square upon 8 pi square Ik, this will have the dimension of temperature and is known as characteristic rotational temperature. So rotational partition function can be written as QR is equal to T divided by sigma theta R. Now for non-linear molecules, that means for polyatomic molecules, depending upon the shape of the molecule, we will have different expression for different types of molecule. For spherically top, where the moment of inertia is equal, IA is equal to IB is equal to IC along all the three axes. If the moment of inertia is same, we will have this expression in which we have root of pi upon sigma 8 pi square I kT upon h square raised to 3 by 2. Now if the molecule are of symmetric top type, that means moment of inertia IA and IB will be same but IC will be different, then it will be root pi upon sigma 8 pi square I kT upon h square 8 pi square I kT upon h square to the power half. And for asymmetric top, where IA, IB, IC, all the three are different, we have root pi by sigma 8 pi square I kT upon h square to the power half, 8 pi square I kT upon h square to the power half and 8 pi square I kT h square upon raised to the power half. For IA, IB and IC, different terms will be used and it can be written as a product which will give the value of QR. Summary of rotational partition function. Rotational energy is given by ER is equal to Jj plus 1 h square upon 8 pi square I, where J is rotational quantum number having values 0, 1, 2, 3, etc. I is moment of inertia which is given by I is equal to mu r square. Mu is reduced mass which is given by m1 into m2 divided by m1 plus m2. Statistical weight factor for rotational energy level is GR is equal to 2J plus 1. Again, J is the rotational quantum number. Rotational partition function, we have seen for linear molecule, we have a different expression, and for non-linear molecules, depending upon whether it is spherical, symmetric or asymmetric top, we will have this type of expression. Now let's see numerical based on rotational partition function. Calculate the rotational partition function of oxygen molecule at 300 Kelvin given bond length of oxygen molecule is 1.2074 angstrom. Now I is equal to mu r square, where r is the bond length. We have converting this angstrom into the SI unit meter. So this will be 1.2074 into 10 to the power minus 10 meter. Mass of oxygen atom is taken as 15.99. We are taking approximately here 16. So we can calculate the reduced mass of oxygen molecule, m1 into m2 divided by m1 plus m2. We are taking 16 into 16 divided by 16 plus 16 into 10 to the power minus 6 and 10 to the power minus 3, converting it in grams. Then we have to divide it by 6.023 into 10 to the power 23. This is for conversion to kg. So on calculating moment of inertia by substituting the value of mu and r, we will get the value of I 1.937 into 10 to the power minus 46 kg per meter, kg meter square. This is the value for Planck constant and this is for Boltzmann constant. We will substitute all the values. We will get the value for partition function for rotational as 72. In case of translational, we have seen that it was of the order 10 to the power 28. That much thermally accessible states are accessible. But here comparatively there are less number of thermally accessible states. It will be the order of 10 to the power 2. 10 to 10 to the power 2. So here we have only 72 thermally accessible states.
Now let's discuss about vibrational partition function. We have seen that vibrational degrees of freedom for linear and non-linear is different, because we know that translational partition function or translational degree of freedom, that is 3. Rotational in linear we have 2, and for non-linear we have 3. And total degree of freedom in a molecule containing n atoms is 3n. Out of this, 3 is translational degree of freedom. For linear it is 2 and non-linear 3. So for linear 3 plus 2, that means 5 consists of translation and rotation. Out of this 3n, we will subtract this 5 and we will get the vibrational degree of freedom. For non-linear, we see that translation is 3, rotational is 3, 3 plus 3 it is 6. So we have 3n minus 6 degree of freedom. According to this, we will get the partition function, whether it is linear or non-linear, or what is the degree of modes of partition. Now let's see vibrational partition function. As we have seen in translational and rotational, vibrational partition function is represented by summation 0 to infinity statistical weight factor of vibrational energy e to the power minus EV vibrational energy level upon kT. Here again we require the statistical weight factor or the degeneracy and the value of vibrational energy. The statistical weight factor for this is 1. Vibrational energy, as we have seen in quantum mechanics on solving Schrodinger wave equation for diatomic molecules considered as simple harmonic oscillator, we get V plus half h nu, where V is vibrational quantum number and has values 0, 1, 2, 3, etc. Here h is Planck's constant, nu is vibrational frequency, which is given by 1 by 2 pi root k upon mu, where k is force constant and mu is reduced mass. Here we see that if we substitute V is equal to 0, that is the lowest energy level, then the energy is not equal to 0. So we will see when we substitute V is equal to 0, it has residual energy which is equal to half h nu, and this is known as 0 point energy. Let us number the equations. Equation number 1, 2 and 3. These are the main equation. Now instead of h nu, we can also write nu is equal to, in terms of wave number, it is c nu bar. Here we will write for nu r omega bar. This is equilibrium frequency in centimeter inverse. So if we take, you have seen that this EV is in excess of the lowest. That means we have to subtract the 0 point energy from this equation. So the corrected value will be V plus half h nu or hc nu bar. Okay, instead of nu we can write c nu bar, where c is velocity of light, minus the 0 point energy, that is hc nu bar. Okay, so we get V hc nu bar as the vibrational energy in centimeter inverse. We will substitute this equation number 4 and equation number 2 in this equation number 1. So what we will get, QV is equal to summation 0 to infinity, GV is 1, we have e to the power, this is the energy in excess of the lowest, upon kT. Here we see that the value hc omega bar, this is very high in comparison to the thermal energy. So here we cannot take this as closely spaced. This hc or h nu or hc omega bar is very higher in comparison to the thermal energy. So we cannot replace this in summation by integration. It will remain as summation itself. Now let us simplify this equation. Let us substitute a constant for hc omega bar upon kT. Let us substitute it as x. Okay, these are all constant for a given temperature and for a given molecule. So we have QV is equal to summation 0 to infinity e to the power minus Vx. Substituting the value of the vibrational quantum number 0, 1, 2, 3, etc., we get this is equal to 1 plus e to the power minus x plus e to the power minus 2x and so on. Or in general form we can write e to the power 1 minus e to the power minus x inverse 1, or 1 divided by 1 minus e to the power minus x. We can substitute the value of x here. So the expression will become 1 minus e to the power minus x is hc omega bar upon kT raised to minus 1. If we substitute the constants of h, c and Boltzmann constant, all these are constants, we can write h c upon k. If we substitute the values of all these constants, this is Planck constant, this is velocity of light, and this is Boltzmann constant, this comes out to be 1.439. So this QV can be written as 1 minus e to the power 1, this is minus 1.439. We are left with omega bar and t. Here if we see this term h C omega bar upon KT. These are all constant for given molecule, and for this we can write a single term, that is theta V, because it has the dimension of temperature. So this can be written as theta V. This is known as characteristic vibrational temperature. In rotational also, if you see, QR is equal to 8 pi square I KT upon h square. In rotational partition function, we see QR is equal to 8 pi square I KT divided by sigma x square. Here also this term has dimension of inverse of temperature. That means h square upon 8 pi square I K. This can be written as theta R, which is known as characteristic. This is known as characteristic rotational temperature. Okay, so we can write this equation as T sigma theta. So this is about the rotational partition function, which has the characteristic rotational temperature, and in vibrational we can write the term characteristic vibrational temperature. Now this is for diatomic molecule taken as simple harmonic oscillator, where there is only how many vibrational modes? For linear, this is the equation. For diatomic molecule, n is equal to 2. That means 3 into 2 minus 5. That is 6 minus 5, 1. Now for polyatomic molecule, according to the degree of freedom, whether it is linear, for linear it is 3n minus 5. For non-linear it is 3n minus 6. We have to take the product of over all the, so we will have for polyatomic molecule, we will have the partition function product of over all the modes of vibration, whether it is 3n minus 5 or 3n minus 6. So this is all about the vibrational partition function.
Now let's see the summary of vibrational partition function. Vibrational energy EV is equal to V plus half h nu, where V is vibrational quantum which has values 0, 1, 2, 3, etc. Nu is vibrational frequency. Nu is equal to C nu bar, where C is velocity of light and nu bar is the vibrational frequency in centimeter inverse. Now we take the energy in excess of the lowest. In case of vibrational energy, we know that the lowest energy level V is equal to 0. The energy is not equal to 0. E0 is equal to 0 plus half h nu. That means the residual value is half h nu, and this is known as 0 point energy. It can be written as half hc nu bar. The statistical weight factor for vibrational energy level is 1. Now for diatomic molecule, we have seen that the vibrational partition function comes out to be QV is equal to 1 divided by 1 minus e to the power minus hc omega bar upon kT. This hc omega bar upon k, this has the dimension of temperature, which can be written as the characteristic vibrational temperature. Okay. So we can write it as theta by T also here. Now if we put the values of hc and k on the constants, it comes out to be 1.439. So we can write for this hc upon k, QV is equal to 1 divided by 1 minus e to the power minus 1.439 omega bar upon T. This is for diatomic molecule. Now for polyatomic molecule, depending upon the number of modes of vibration, whether it is 3n minus 5 or 3n minus 6, we will carry out the product over all the vibrational modes and we will get the total vibrational partition function. Let's see a numerical based on vibrational partition function. Calculate the vibrational partition function of oxygen molecule at 300 Kelvin. The vibrational frequency for oxygen is given 1580 centimeter inverse. So this is given in centimeter inverse. This is the vibrational frequency. We know the value of Planck's constant, Boltzmann constant and velocity of light. We will substitute it in this equation. QV is equal to 1 divided by, just you can take this formula, 1 minus e to the power minus 1.439 omega bar upon T, because we know Hc upon K is 1.439. On substituting the value, we will see that the number of thermally accessible state is very less as compared to the rotational and translation. In the translation we have seen it is 10 to the power 28. In rotational it was 72. Here it has come around 1. Okay. Now electronic partition function. Electronic partition function is given by Q is equal to summation 0 to infinity GE e to the power minus EE upon KT. And the statistical weight factor is given by GE is equal to 2J plus 1. Here J is not the rotational quantum number, it is the total angular momentum quantum number, which is given by J is equal to L plus S, where L is the orbital angular quantum number and S is the spin quantum number. L can have value 0, 1, 2, 3, etc. S has value plus half and minus half. So accordingly we will have S, capital S is equal to 0 or half or 1 depending upon the number of unpaired electrons in the outermost energy level. So we can write QE as G0 e to the power E0 plus KT plus G1 e to the power E1 plus KT plus G2 and so on. This is plus dash dash dash. At room temperature, most of the molecules occupy the ground electronic energy level because the excited electronic energy levels are so far above the ground state. So we can neglect the contribution from all these excited states. So neglecting the contributions of excited state, we have electronic partition function QE is equal to G0 e to the power minus E0 upon KT. All this term will be neglected. Now for ground state, if the reference state is taken as 0, EE will be equal to 0 and the statistical weight factor will be represented by G0. So QE will be equal to G0 e to the power 0 and e to the power 0 is nothing but 1. So we have QE is equal to the degeneracy of the ground energy level, which is given by 2J plus 1, which will be different for different atoms. If we consider the ground electronic states of free atoms, they are generally degenerate. Let us see few examples. For hydrogen, S is equal to half, L is equal to 0, J will be equal to half and G0 will be equal to 2, so QE will be equal to 2. For helium, S is equal to 0, L is equal to 0, J will be equal to 0 and G0 will be 1, so QE will be 1. For chlorine, GE is equal to 4, therefore QE will be equal to 4. For alkali atoms, it is same as that of hydrogen atom, GE is equal to 2, QE will be equal to 2. Now in case of molecules, we see that the ground electronic states for most molecules are generally non-degenerate, that is they are singlet. G0 is equal to 1, QE is equal to 1. Ground electronic state of most molecules are non-degenerate, that is are singlet. Exception is oxygen molecule, for which GE is equal to 3, therefore QE will be 3. Similarly, NO molecule, GE is equal to 2, therefore the partition function of electronic partition function will be 2 in this case. But generally we neglect this because we take QE is equal to 1. For atoms like chlorine and molecules like O2 and NO, the difference between the ground state and the first excited state is small. Therefore, we have to calculate the partition function taking in account the contribution of the first excited state. Here we see the example of chlorine atom. the term symbol for chlorine atom. For ground state it is 2p3 by 2, and for first excited state the value of J is 1 by 2. So J is 3 by 2. So G0 will be equal to 2 into J plus 1, that is 4. J is equal to half. So G1 will be equal to 2 into half plus 1, that is 2. Okay. Now for the first energy level the energy is 0. Second, the energy gap between the two can be written as h nu or hc nu bar, where c is velocity of light and nu bar is the frequency in wave number. Now from the electronic spectra of chlorine atom we see that the frequency separation between the lines is equal to 881 centimeter inverse. So we will substitute the value here. Here it will be e to the power 0. The degeneracy here is 4. 4 into e to the power 0. This is 1. So this will be 4. Degeneracy for the first excited is 2. E to the power. This value is nu bar is 881 Hc upon Kt. We have already seen that Hc upon K is equal to 1.439. We will substitute the value for the temperature. Let us take for 1000 Kelvin. On substituting the value and calculating the exponential, we get the value equal to 4.56. So generally QE is equal to 1, but there are exceptions for atoms like chlorine and molecules like oxygen and NO, where the QE can be greater than 1. Summary of electronic partition function. Electronic energy for the ground state is taken as E0 equal to 0, and for the first excited state we can write delta E is equal to h nu or hc nu bar. Statistical weight factor is given by 2j plus 1, where j is the total angular momentum quantum number. Electronic partition function can be written as QE is equal to summation 0 to infinity 2j plus 1 e to the power minus EE upon Kt. But we know that at room temperature most molecules occupy only the ground electronic energy level and is considered to be occupied as excited electronic energy levels are so far above the ground state. So there will be only contribution from the ground electronic state and there will be no contribution of the electronic excited states. Therefore, electronic partition function is generally equal to the degeneracy of the ground state, which is written as QE is equal to G0, which is equal to 2J plus 1. Now let's say numerical based on electronic partition function. Calculate the electronic partition function of hydrogen molecule at 300 Kelvin. The lowest electronic energy level of hydrogen is near minus 32 electron volt and next level is 5 electron volt higher. For solving this, we will take the minus 32 electron volt, the ground state, as a reference and we take the value as 0. We know the values of Planck constant, Boltzmann constant and velocity of light. We will substitute this in the equation. QE is equal to summation 2j plus 1 e to the power E upon Kt. Here it is the electronic energy level. 2j plus 1j is the total angular momentum quantum number. We will substitute the value in this. On opening this, we will have the ground state plus the other excited state. We know that all the terms except the first are nearly 0. So all the other terms will be neglected. And the first term is e to the power 0. So we have 2j plus 1 e to the power 0. E to the power 0 is 1. And the value of J, total angular momentum quantum number for hydrogen in ground state, is 1 by 2. So we will have G0 is equal to 2 into half plus 1, that is equal to 1. Hence on solving this equation we get QE or the partition function equal to 1. Generally we see that for the molecules the electronic partition function is equal to 1. There are exceptions in this case, like that. For example, we have seen in the case of oxygen molecule and NO molecule. Now expressions for molecular partition function and their order of magnitude of thermally accessible states. Translation partition function, it is given by Qt is equal to 2 pi mkt to the power 3 by 2 h cube upon into V. For rotational, we have different expression for linear and non-linear. And for vibrational partition function, this is for diatomic molecule, and for where there is more than one vibrational modes, we will use this formula, and this is the formula for the electronic partition function. The thermally accessible states, if you will see how many states are thermally accessible, or number of states that will be occupied at a given temperature is very high in case of translational energy level, comparatively less in case of rotational, 10 to 100. Vibrational, we will have far less, and for electronic there will be equal to 1. This will be 1 to 10 and this will be 1. There are exceptions in all cases. So the total partition function, the order of thermally accessible states we have seen. For translation it is larger than rotational, then vibrational, then electronic. Total partition function will be the product of various partition function components. For atoms, we will have only translational and electronic contributions. So Q will be equal to Qt into Qe. In case of molecules, it will have all the contributions of Qt, Qr, Qv and Qe. So we have to take the product of all the components. So this is all about the various contributions of partition function towards the total partition function. Thank you very much.